So coming up here is a professor of astronomy, professor of history, Professor Gregory Stitz.
All right, well, thank you all for coming out tonight, and this is just some basic History of Science 101, or actually 122 material. So, as you may know, Plato insisted that heavenly bodies move in perfect circles at uniform speed. Well, why must they do that? Why do we know that they do that? Well, if you just take it as a starting point that the heavens are perfect, unlike the earth, and it's the world of pure form. As you may know, Plato had this idea that what we see on Earth is this kind of pale reflection, partial reflection of the true forms, and so clearly the circle is the most perfect form because it has a constant curvature with no end, and therefore clearly the heavenly bodies that move, i.e., the planets, must move in perfect circles at constant speed. But obviously, if we look at the night sky, even without the aid of telescopes or something like that, and as the Babylonians, for example, did and wrote it down in great detail, and Greeks eventually got that information as well as Egyptian records. How do we explain what we actually see? Something like retrograde motion. And so a contemporary of Plato's came up with this ingenious idea that, well, why don't we have a kind of a nested sphere situation like this that could account for at least basically what you see with retrograde motion. And once we start moving in that direction, it turns out that if we were to assign 4 spheres to each of the planets, each moving in a different direction but at a steady but different speed, it's kind of close to the observations, and we might need to add a few more to make it a little bit more precise. And by the time we get to Aristotle, so Plato's student, we get up to about 55 spheres, at least in most of the systems. It's kind of cumbersome. And so this is Aristotle's cosmology. It's Aristotelian cosmology. It's actually not, as we have seen, this idea originates in Plato's time, but by Aristotle's time, it's gotten fairly complicated. And in addition, so with the Earth is in the center, the Moon, of course, in those days is thought of as a planet, and the others, and each is carried in a crystalline sphere. Well, actually, as you see, each has at least 4 crystalline spheres to which it is attached. And so this is a philosophical concept. In other words, you can, by putting in extra spheres, as many as 55, actually try to make it match the observed motions of the planets. But in its basic simplified form, it's essentially a philosophical concept, i.e., an aesthetic concept. And indeed, as probably many of you know, aesthetics plays a big role in kicking off scientific ideas. Often the aesthetic concept is a starting point that people take as an axiom or something like that. Well, much later, not because this was really necessary, Christianity, the Roman Catholic Church in particular, adopted Aristotle's cosmology, and so it also becomes a religious tenet. And Ptolemy, we've already, his name has come up, around 100 in the Common Era, was mainly an astrologer. And so he needs to cast horoscopes, and he is interested in where the planets are and where they're going to be in particular. So there's this tension between this beautiful philosophical model that doesn't actually tell us where the planets are so well, or if you're an astrologer, which most astronomers were also astrologers in these days, then you need to know where the planets were, are, or are going to be. And so Ptolemy took Greek astronomy and he developed it into a complete system for tracing and predicting the motions of heavenly bodies. And yet, within the constraint of being able to know where the planets are going to be, he tried to so-called what we call save the appearances. And so we want to save the appearances of where the planets actually are, and we also want to save as much as we can of the philosophical model. So circular motion, a geocentric universe. And by the way, on that point, some Greek philosophers did propose that that planets moved around the sun, but that was discussed by some people and regarded as absurd. And so generally it's geocentric and uniform motion. So how do you do that? Well, these are the basic things that you have to work with. You can take the Earth, and although it really should be the absolute center, just move it off to the side, and then draw a circle here on this center, and that's the deferent circle. And then you put an epicycle on it, a circle revolving around the deferent, carried by the deferent would be the typical language. You can actually have an epicycle on an epicycle. So occasionally you will need that. And you can also have an equant point, which is approximately the same distance from the center, but except opposite the Earth. And if you mix those together in various ways, you can get a pretty good, especially for those days, a pretty good approximation of where the planets are going to move. So you have this eccentric epicycles on deference, eccentric positions, and equant points, which is essentially the same thing, just mirrored across. And so this is how it would basically work. And it was good to within about 2 degrees, which was good enough for many centuries. In fact, this lasts into the 17th century before it starts to break down, and you get in the late 16th century, you get Tycho Brahe. He had the very best naked eye observations, and then in the 17th century you get telescopes and the Copernican system, and eventually it all starts to change. But here's what it would look like in a textbook. This one's from 1550. This is the Ptolemaic system in the Almagest, which is actually an Arabic term for the magisterial, all-encompassing system. And you can already see just from these textbook pages how this could become rather complicated if you're trying to actually get this down to where you yourself can predict the planetary motion. And here, for example, is the model for the planet Mercury in the Ptolemaic system. So you can read the fine print here, but it takes quite a lot to figure out where Mercury is going to move if you think that the Earth is more or less the center of the universe and everything is moving in circles at a constant motion. This Ptolemaic system did get translated into Arabic, and so it moves into the Islamic Middle East, and there it gets tweaked, and some very ingenious little tweaks that I don't have on here, but essentially that nobody, even in the Islamic world, ever thought to question the basic fundamental notions. So this will persist until the 17th century. All right, well, that's all.
Another elegant solution. Would the sun-centered system ever have occurred to somebody else? The best and the most elegant way, instead of the cycloid. I'm amazed that it didn't seem it's kind of obvious that it was a more elegant system to just think of as being all to itself.
Yes. Oh, okay. So, why didn't somebody in all these centuries, because you see something absurdly complicated like this, why didn't somebody think that it's just, make everything orbiting the sun, and wouldn't that help make things a little bit better? And so, first of all, I mean, I can't quite answer it because I don't know why, but people were very much bothered by this, philosophically. I mean, and they would say that, and say this is just weird. It's it gets us, it works, good enough, but it seems like it really shouldn't. The cosmos doesn't work like this, and so Copernicus, of course, comes up with this heliocentric system, but because he continues to use circular orbits and a steady velocity, steady speed, then he ultimately can't make it a whole lot better. In fact, it's arguably no better than the Ptolemaic system. Not any more accurate, not even necessarily any simpler. Probably so Tycho Brahe, the Danish astronomer, came up with this sort of ingenious idea. He said the moon revolves around the Earth, and the sun revolves around the Earth, and all the other planets revolve around the sun. And that was a little bit simpler and a little bit more accurate than the Copernican system. So I guess you could say that finally somebody sort of thought of that, but not entirely. Yeah. Why it took so long? Well, it's hard to say it. If I had to venture a guess, I would say because the Ptolemaic system was entrenched and it worked good enough.
It's still tied up to the Platonic idea that things have to move in certain, have to move velocity. Not the skies were perfect.
Yes, I think so. I mean, so my specialty is actually the history of geology, and geology was not even a discipline for a very long time because the Earth was considered to be, of course, dirty and sort of the imperfect place, and it's not going to last that long anyway. It's about to, it's any day now. It's going to come to an end, and so it's only in the late 16th, early 17th century that people start to take the Earth seriously as an object of study. So it's probably connected, the aesthetically.
So I have a question too.
So do you know if this was if people believe that this is physically, that planets are physically moving around in this difference, or like in these epicycles, or do they try to see this as more of a mathematical method to solve the problem? Not that this is physically what is going on, but just this is how we can actually solve this problem.
Yes, for the most part, it's the latter. In other words, this is a mathematical device that causes us to figure out where they are. They couldn't really be doing that, but yeah.
I was just wondering, someone asked earlier about why didn't we discover that earlier? Why did someone come up with why we have to be Earth-centric? Well, religion has a lot to do with keeping it Earth-centric. So that's why it's delayed, I think.
Right. Well, so the suggestion that it was religion, and eventually it sort of does become that way after Galileo, but Galileo, it was a very complicated story of his. It wasn't strictly speaking a religious issue. There were. There were occasionally people who would come up with the idea that maybe the Earth is moving around the sun. I mean, after all, it's possible. And then people would debate, well, if that were the case, what about, why don't we see parallax? That was something that people would say very early on. And they'd say, well, people would often add up, Earth going around the sun versus sun going around the Earth. And, they kept concluding that, no, it looks like the Earth is the center of things. And then religiously, of course, too. Yeah, especially after Galileo. That kind of...
Was it Galileo under house arrest?
Well, yeah, he was, but it was a little more complicated.
But he was a nasty character, actually.
He rubbed people the wrong way because he said, I'm smarter than you are, and then he would prove it. And and he particularly was disliked by the Jesuits, and there was this power struggle at that time. It's connected with the 30 Years' War and Pope Urban VIII's policies in the 30 Years' War. Eventually, Pope Urban VIII, who was Galileo's protector for a while, fell. I mean, he was still the Pope, but he had to defer to Galileo's enemies, and the Jesuits came back into power. And so there's a lot more to it than just purely a religious or mathematical or astronomical issue, but because Galileo was so famous, then at that point it becomes in areas that were not so much Catholic but Jesuit dominated. Then you have to say that the Earth is, that everything revolves around the Earth for religious reasons, even if you privately don't think so.
So we talk a lot about Copernicus being one of the first people to say that the Earth revolves around the sun, everything else revolves around the sun. Were there any other cultures that came up with a similar idea before him or near him, or was he really truly the first person to at least prominently come out and say this?
There were several people in ancient Greece, but I can't remember their names, that advocated a heliocentric universe. And I don't think there were any in China or Japan. May have been somewhere else, but at least there were some ancient Greeks who did.